In this video, we're going to use the creation and annihilation operator A dagger and A, introduced in the previous segment, to generate the energy spectrum of the harmonic oscillator. And this calculation, as we discussed, is going to involve, in a very important way, calculating various commutators of the operators. So what we just proved in the previous video was that the harmonic oscillator Hamiltonian can be represented as a sum of two terms. The first term is A dagger A, where A dagger is this creation operator and A is this annihilation operator. And also there was a second term which is proportional to the commutator x of x and p, position and momentum. And by the way, this commutator of x and p is one of the so-called canonical commutation relations in quantum mechanics, and we actually should have discussed it in more details earlier in the course, but better later than never. So let me just first give you this result for this commutator. This commutator, in fact, is proportional just to so-called C number, or in the early quantum mechanical jargon, or in other words, to the identity operator. So in other words, this commutator of x and p is not an operator at all. It's actually just a constant. And to see this, we can go to the position representation, and let's say in position representation, x times p acting on the wave function psi of x is equal to x, which is just multiplication operator, followed by minus I h bar d over dx acting on psi. And so what we're going to have is minus I h bar psi x psi prime. So this is the result of the action of these two operators in this order. Now, if we consider a different order of the operators, if we first put, x is going to act first, and then we're going to have the momentum. So in this case, we can write it as follows. It's going to be minus I h bar d over dx x times psi. And so in this case, we have to use the chain rule to calculate the derivative of both terms in this product. So it's going to involve, therefore, minus I h bar derivative of x is just 1 psi minus I h bar x psi prime. And now if we put everything together and apply this commutator to an arbitrary function psi of x, so let me actually write it in red. So if we now have x, commutator of x and p sort of acting on a wave function psi, so what it means is that we want to act by the following operator, xp minus px on psi. And so we essentially have to subtract result from this result. And so these two guys are going to cancel each other out, and the only thing which is going to remain is plus I h bar psi. So the action of the commutator of position and momentum on an arbitrary function psi of x is equivalent to multiplying this function by I h bar, which is exactly the result that I advertised in the beginning. And this is, again, perhaps most of you or many of you already knew it. So this is, again, one of the canonical commutation relations in quantum mechanics. Now, to continue this algebraic exercise in calculating commutators, let me now calculate a very useful commutator for the following, namely the commutator of A and A dagger. And this is another so-called canonical commutation relation. Let me write the result first, and then I'm going to prove it. So, and we will see that the commutator of A and A dagger is going to be equal to 1. So to prove this, we use the definition of A and A dagger from the previous video and this commutation relation of position and momentum. So if we calculate A and A dagger, the commutator of A and A dagger, so we will have basically two types of terms. So here we're going to have m omega 2h bar x plus ip 2m omega h bar, and the second term in this commutator is going to be the same thing, but with a minus sign in front of the I. So here it is. And we'll see that we have commutator of x and x, we have commutator of p and p, but of course a commutator of an operator with itself is equal to 0, because of course, for example, x minus xx is equal to 0, right? So any operator commutes with itself. So the only commutators that are going to be non-trivial are going to be these cross commutators of x and p and x. And you can convince yourself that the commutator of x and p is, of course, equal to the minus of a commutator of p and x, because we simply switch the order in which the operators appear. So therefore, we can write it. So this result, so let me just go back to the blue fonts. So it's going to be twice, let's say, the commutator of this guy and this guy. So m omega over 2h bar from this term, minus I 2m omega h bar from this guy, and here we're going to have x and p. But this is something we know, we just calculated it, so this is this commutation relation of position and momentum, and it's equal to I h bar. And so indeed, if we put everything together, we will see that, well, m and omega cancel here, so h bar and h bar under the square root cancels here. So I times minus I gives us 1, and 2 over 2 is equal to 1. So all in all, it's equal to 1 as advertised. So this completes a very important derivation, namely the derivation of the following identity, and it's an operator identity. It doesn't really matter what representation we use, what kind of methods we want to solve. We have proven that the harmonic oscillator Hamiltonian, so let me actually switch to red, the harmonic oscillator Hamiltonian, as written here, can be represented as h omega a dagger a plus 1/2. So this is from this commutator, where the a and a dagger commute to 1. Or in other words, you may see it in the literature, so these annihilation and creation operators satisfy the canonical commutation relations. So the second term in this expression for the Hamiltonian, as we discussed, is just proportional to a number. So cannot possibly affect the solution of the eigenvalue problem. Namely, if we want to solve the equation h psi is equal to e psi, and if psi happens to be an eigen function of a dagger a, so it would indeed be eigenfunction of the whole Hamiltonian h, with a slightly shifted energy, because the identity operator just reproduces the function. So, and therefore, in order for us to find the spectrum of the operator h, in order for us to solve this eigenvalue problem and find the eigenfunctions and eigenvalues, we have to focus on the eigenvalue problem for this operator a dagger a. And now comes a very important part, where we're going to generate the entire energy spectrum of the Hamiltonian from just a single eigenstate of it, or more precisely from an eigenstate of this guy a dagger a. And to generate the spectrum, we would need just two pieces of information: the fact that we can represent the Hamiltonian as so, and the commutation relations between the annihilation and creation operators that we just derived. So at this stage, let me assume that I know an eigenstate of this guy, of a dagger a, and let me call this eigenstate letter case n, and the corresponding eigenvalue will also be n. So this would also, of course, imply that the state n is also a solution to the time-independent Schrödinger equation for the harmonic oscillator Hamiltonian, or in other words, it's also an eigenstate of the Hamiltonian with the energy h omega n plus 1/2. So this is the energy of this state. Now let us examine what happens with this state we assumed exists under the action of this creation and annihilation operators. And of course, what we're interested in is whether or not we can construct new eigenstates out of an existing eigenstate. So first let me act on this n by the operator a dagger, and let's see how this operator behaves with regards to this guy, a dagger a. So, and what we can do here, we can take advantage of the canonical commutation relations that we derived in the previous slide. And using these commutation relations, we can write a dagger as 1 plus a dagger a. So here we're going to have, so basically exchange the order of these two operators. So we're going to have, instead of a dagger, we're going to have a dagger 1 plus a dagger a, acting on n. But, so this is just a number, and this guy, we already know how it acts on n. So by assumption, this is an eigenstate of a dagger a. So therefore, we can write it as a dagger n plus 1/2, plus 1. And since this is an operator and this is just a number, we can just exchange the order. And so we have n plus 1, a dagger n, which is exactly the same function as in the left-hand side. So what we have proven is that if n is an eigenfunction of the operator a dagger a, and consequently if it's an eigenfunction of the operator h, the Hamiltonian, then a dagger is also an eigenfunction, but with an eigenvalue n plus 1. So it raises the energy of the oscillator by one energy quantum, if you want, of h omega. In a very similar way, what we can prove is the following. So we can prove that if n is indeed an eigenfunction of the Hamiltonian, then the action of the annihilation operator on n, so this function, is also an eigenfunction of the Hamiltonian. But it is an eigenfunction with a smaller energy, which sort of justifies the terminology of this being called an annihilation operator. So, well, if we were to repeat this exercise that we just did for a dagger, and if we were to apply a dagger a on this function, we would see, and I leave it for you as an exercise, that this guy is also an eigenstate of a dagger a, but now with the smaller eigenvalue n minus 1. And here I will have the same function. So by knowing an arbitrary eigenfunction of the Hamiltonian, I can construct an infinite number, what seems like an infinite number of other eigenfunctions with different eigenvalues by applying this creation and annihilation operator. And so we can also construct the spectrum of the Hamiltonian, but we haven't yet answered the question of what n could be. But with a little bit of thinking, we can convince ourselves that n here must be an integer going from 0 up to infinity, 0, 1, 2, 3, etc. And a way to see this is essentially via a sanity check, if you want, going back to the physical problem we're trying to solve. So remember that what we're doing here, we're trying to find the energy levels in this harmonic oscillator potential, which is simply the parabolic potential proportional to x squared. So this is v of x proportional to x squared. Now, if we assume that we know a certain eigenfunction with an energy E sub n, as so, and this is, let's say, this corresponds to the state n, then by applying the creation operator a dagger, we can construct a series of higher energy states, so n plus 1, n plus 2, n plus 3, etc. And there is no problem with that. But also by applying a, we can lower the energy, and we can do so seemingly indefinitely. But clearly, this procedure has to stop somewhere because we cannot go below 0. So in other words, we cannot go below the minimum of the potential, which in this case is 0. And this also implies that, therefore, this procedure of generating new eigenfunctions using this annihilation operator must terminate, and so there must exist, therefore, basically the ground state for which the action of the annihilation operator simply is equal to 0. Okay, or in other words, so this guy, the vacuum state, is the eigenstate of this guy, A dagger A, with the eigenvalue being 0. Or using this result, so the energy of the ground state therefore is equal to h omega over 2, which is the so-called vacuum energy of the harmonic oscillator. But this is really important, and this tells us that this is really the property of the ground state. Okay, and this is, by the way, the simplest way to find an analytical expression for the ground state. We simply have to find a function that is annihilated by this operator. And finding this function is really the only remaining step in completing the derivation, because here we essentially have done everything which needs to be done. We found a series of energy levels, so let me just write it again. So E sub n, the energy levels of the harmonic oscillator, is equal to h omega n plus 1/2, where n is equal to 0, 1, 2, etc. And this was constructed under the assumption that an eigen state exists. But we haven't yet shown that it is indeed so. We haven't yet constructed explicitly the eigenstate. And this is really the last piece of the puzzle that we will put together in the next video, where we also will summarize all the findings about the harmonic oscillator and go a little closer to physical reality from this abstract algebraic derivation, which, however, I hope shows the power of this algebraic method. So here again we are solving initially what looks like a differential equation, but we get the results and the quantization of the energies without even calculating any derivatives. It's all based on these commutation relations, and well, I find it very elegant, and I hope some of you also enjoyed this derivation. But there is more to do.